Hi, I want to talk about the fundamental aspects of quantum mechanics and really what we sort of refer to in general as wave mechanics. And what quantum mechanics tells us is whenever we have interactions happening where those interactions by some condition, boundary condition, external factor are limited to exist in a finite region of space, the interactions between an object and its surroundings are quantized. There are discrete energy levels at which those interactions can happen. So, to gain an understanding of what happens, we need to start thinking about physics and interactions probabilistically. And rather than saying an object A crashed into an object B, we talk about calculating relative frequencies of occurrences of events based on treating the location of an object as being a probability wave that can evolve in space and time. Where if we were to take a look out through all of space, then at any given time we would see an interaction happen somewhere there, but we aren't necessarily guaranteed to observe it in any one specific point. So to do that, we need to talk about probability wave functions. And the symbol we use in that for physics is a capital Greek letter psi, and it could be a function of x, y, z, and time. We're going to restrict ourselves to one spatial dimension and time. And that would give us capital psi of x and t, but we're also going to further simplify things by coming up with scenarios where space and time are independent of each other, what we call a time-independent wave function. So we could write this as a function in space, lowercase psi, of x, and some function of time. And we could examine that by thinking about waves we've already looked at, electromagnetic waves. So with an electromagnetic wave heading out through space, we have an electric field that's oscillating as a function of space and time. And if there are no obstructions, everything's just moving along as a plane wave, then our electric field as a function of space and time would be written as the amplitude of our electric field times the sine of kx minus omega t, where k is our angular wave number, 2 pi divided by the wavelength, and omega is our angular frequency, 2 pi divided by the period of that wave. Well, for expressing waves for the purpose of quantum mechanics, we use complex numbers. And complex numbers are just the math of making use of a two-dimensional number line. So instead of just real numbers, we have an imaginary axis where every number is multiplied by the square root of -1. And we could work in that using Euler's angle. If you take Euler's number e raised to the square root of -1 times an angle theta, e to the I theta is equal to the cosine of that angle theta plus the square root of 1 times the sine of that angle theta. It also means you could take sine and cosine and express them in terms of Euler's number, e to the I theta. So instead of writing this as e to the sine kx minus omega t, we could write this as e, our amplitude, times Euler's number e to the square root of -1 times our angular wave number k times our location x times e to the minus I omega t. It's the same as e to the ikx minus omega t if we're sort of multiplying I by kx minus omega t as a quantity, but those two terms are really independent of each other. So for time-independent interactions, we're just going to say everything evolves sinusoidally through time, and we're not going to worry about time at all moving forward. We're just going to take a look at things that affect what's going on in space. Now, if I just have a free wave, free plane wave moving through, that light would make itself known to anything that gets in its way. But if I put in an obstruction, like say a small opening or two small slits close to each other, then I end up getting shapes to that wave amplitude, where I have alternating regions of high electric field intensity, no electric field intensity, and that creates the diffraction and interference patterns talked about when we talked about with light. Well, that's essentially what happens with all interactions. If there is some interaction with an object that can be treated as a wave, and from Du Bois' work, all objects have an associated wavelength as long as we have the correct sizes in order for that quantum interaction to happen, we can end up seeing space interact probabilistically. Now, to figure out where we would get bright spots or dark spots in a diffraction pattern with light, we had to calculate intensities. We squared the electric field. Well, if we're working in complex functions, we can't just square things, because we would end up with a term in the middle that doesn't cancel out. So instead, to find the magnitude, we take the complex conjugate of a function and multiply by our original function. So a complex conjugate, we take all of the square roots of -1 that we see, and we replace them with a minus sign. And if we have minus I, we would replace it with plus I. So the complex conjugate of this would be e to the minus I theta, which would be the cosine of theta minus I times the sine of theta. So if I multiply that, cosine times cosine gives me cosine squared. I would get plus I sine theta cosine theta minus I sine theta cosine theta. The square root of -1 terms cancel out, and then I would get minus I squared sine squared theta. Well, I squared is -1, minus -1 gives me cosine squared plus sine squared, which equals 1 in amplitude. That dependence goes away. All complex conjugates work exactly the same way. Now, some wave functions, a lot of wave functions, are totally real. An example of a probability wave is, say that I'm just going to walk back and forth, aimlessly pacing, and at some point I release my hand. Well, there might be equal likelihood that I were to release my hand at any given point. So if I were to repeat that experiment billions and billions of times, my probability function would look something like this, where there's a possibility of the event happening, and then all of a sudden things go away. Now, this wouldn't be necessarily good for a quantum system, but something that we would see in some quantum systems are functions that look like this. This is the Gaussian curve, where this function is equal to some maximum value a times Euler's number to the minus a constant little a times my position squared. As x goes to infinity, this goes to 0 very rapidly. As x goes to minus infinity, this goes to 0 very rapidly, symmetric about the ends. But what we would see happening are most of the interactions occurring near the middle, and then the farther away we go, the more rare it would be to see an interaction. And if you had some statistics and talked about things like uncertainties, or 67% of the time, 95% of the time, 99% of the time, n number of sigmas, well, you're looking at a very, very, very similar mathematical piece to the math that we see in quantum mechanics. And throughout the final chapters of this course, we're going to dive into these concepts in a lot more detail. Thanks for watching.